todos. Desculpem o problema que nós tivemos aí, problemas técnicos, mas graças a Deus foi resolvido. E eu vou falar com vocês agora em português. Por favor, vocês que estão aí na sala, convidem-se alguma pessoa aí que não foi avisada. A gente fez esse aviso em cima da hora, porque ontem nós decidimos fazer essa apresentação, percebendo a importância dessa apresentação que eles tinham trazido para nós, com muito carinho, né? Então, nós estamos com dois diretores importantes do nosso convênio, fazem parte do convênio com a Batelle, e é a primeira iniciativa que está indo à frente com o nosso centro de reatores de pesquisas. Então, já é a segunda visita que a gente recebe, eles estão visitando vários centros, houve um contato com alguns gerentes que já estão envolvidos no programa, e eles vão fazer 2 visitas ainda hoje. Eles estão muito abertos à cooperação. Tivemos uma reunião ontem onde eles colocaram várias propostas de temas de cooperação. Então, a gente tem que aproveitar essa oportunidade onde está vendo essa grande colaboração mesmo na prática, né? E eles abrindo espaço para que nós vamos visitá-los e também aprender tecnologias avançadas lá, como recebê-los aqui. Isso tudo com o apoio da Batelle, através daquele convênio que foi assinado. Nós queremos agradecer mais uma vez a internacionalização, a pessoa do Dr. Nicolau, que está aqui assistindo, pelo grande esforço que foi feito no começo para se estabelecer isso, a busca através dos pesquisadores, e é uma grande satisfação dizermos que temos isso indo, de fato, numa direção do que a gente imaginava. Então, vamos aproveitar. E, então, a apresentação vai ser sobre o Idaho National Laboratory Nuclear Facility. Vou mostrar para nós o que eles têm, e os pesquisadores, diretores estão aqui, é o Dr. Ronald A e o Dr. Ronald A. Então, fiquem à vontade para anotar, após a apresentação deles, se tiverem questões, vocês, por favor, fiquem à vontade para nos mandar ou perguntar, vocês mesmos, logo após essa apresentação. E, se tiverem condição, chamem mais ou anotem para que vocês compartilhem isso com os colegas, tá? Eu queria passar a palavra antes para o Dr. Frederico, porque ele está intensamente envolvido nessas ações iniciais com a Batelle. Então, eu queria que ele falasse alguma coisa sobre como é que está sendo conduzido. E se Niklaus quiser falar algumas coisas, Niklaus, eu quero salientar que isso é também isso é um resultado do grande esforço que tem sido feito pela internacionalização do IPEN e o grande dedicação para que esses convênios vão à frente. Obrigada.
Obrigado, Isolda. Obrigado aí pela presença de todos. Só queria avisar que isso vai ficar gravado. Nós vamos colocar depois o link no site do IPEN, vou combinar com o Edivaldo, ele vai divulgar no momento apropriado. Como a Isolda disse, acho que eles estão com muita disponibilidade para cooperar, e são 2 diretores muito importantes aqui, são pessoas muito conhecidas na área de reatores de pesquisa, né? O Ronald A, diretor do Complexo de Testes de Materiais de Combustível, e o Ronald A, diretor do Complexo de Testes de Eventos. Então, eu vou passar a apresentação a eles, e a gente está aberto aqui depois para interação. Assim que eles terminarem, seria muito interessante quem puder interagir com eles, acho que é uma grande oportunidade. Um momentinho só. Isso é tudo, né? Isso.
Agora, acho que essa é a primeira.
Let's see if this works. Yes. All right. Excellent.
Thank you.
All right. Good morning, and thank you very much for having us. As the introduction, my name is Ron Cron, and this is Sean O'Kelly. We work at the Idaho National Lab, which is the United States National Nuclear Lab. And Idaho National Lab is in the Pacific Northwest version in our country, and our facilities are out in the desert. And the history in the facilities is we have built 52 nuclear reactors for demonstration. We are an applied engineering lab, so Not as much theory and more actually building, construction, engineering, and experiments. The first nuclear power plant in the world was built on the Idaho National Lab, and it powered a small town just west of our site called Arco. It also was the home of our naval reactors training facilities and prototype reactors for many, many years. Since that time, we've evolved where, I'm going to see if I can coordinate this. Our mission has gone beyond nuclear, and it's more energy delivery. Obviously, the world is facing all types of energy and climate, that nexus. We believe our lab is positioned to solve those types of problems in a leading way. And our mission is to discover, demonstrate, and secure innovative nuclear energy solutions. So it's not just provide the energy, but also show how you can use nuclear energy in a different way than just hooking it up to the grid, and provide the cybersecurity such that it cannot be hacked. All right. You jump in anytime you want. Our site is very large.
You're not changing that one.
Oops, thank you. I am changing this one. I'm just going the wrong direction. Okay, let's see if we can coordinate this. We're gonna do this. We have the team up here. So our site, it's hard for me to hold still when I'm presenting. I'm usually standing, moving all around. Our site is 890 square miles. So it provides an opportunity when you have a site that large and you have 5,400 employees, and 600 and some vehicles in our fleet, where we can really demonstrate in a fundamental way how you may be able to do energy delivery at scale without ever leaving the boundary of the government complex. I will use the pointer real quick, or no, I won't. There we go. So this is where the city of Idaho Falls is to the east. And then out on the desert site, first you run into the Materials and Fuels Complex, which I'm the director, and then you go out the Advanced Test Reactor. There are also other, there's a Naval Reactors facility, and then there's another facility that does materials work for the Department of Defense. Organizationally, there are 5 directorates at the Idaho National Lab. Sean, oh my goodness, I need training on the device here. So I run the Materials and Fuels Complex. Sean runs the Advanced Test Reactor. There's also a Nuclear Science and Technology organization. That organization does a lot of modeling and simulation. They do controls work for human factors. They also do a program to try to sustain the nuclear fleet in the United States called a light water reactor sustainability. And they do all the programmatic interface with our Department of Energy. There's also 2 others, Energy and Environment, Science and Technology, EES&T, is looking at how to bring all the different power sources onto the grid together in harmony. Now that you have more and more solar and wind, which affect the grid in a much different way. And they're looking at what we call hybrid energy solutions, where, for example, right now we're running a project with a nuclear power plant I used to work at, where they're going to be producing hydrogen on site at that nuclear power plant using the electric generated from the plant. And then National Homeland Security, our expertise is cybersecurity from a systems engineering perspective. So protecting pipelines, the grid, information systems, all the things you think of as your normal infrastructure that you take for granted that are now run by computers, how to keep those, protected from being hacked and taken over. All right. I did it again. Let's just keep my fingers off of that one. Here are some examples of some work that's being done relative to the nuclear mission. So we work on nuclear, we'll get into more details, nuclear materials and fuels. We do have a high performance computer. So we do bring advanced computer modeling sim. We also do some work for NASA. We generate the radioisotope thermoelectric generators for the Mars rovers and for the Voyager mission. for the deep space missions. And we have an idea of building new advanced test reactors. We are currently working on 3 reactors on my site right now, what we call micro reactors, so 10 megawatts or less. We believe that the future still includes large power plants, the 1,000 megawatt version. We also believe that small modular reactors will help the United States replace the coal plants that are being retired. And we believe these micro reactors will, at places that are off the grid, and our Department of Defense likes the idea of having a reactor they can transport and not have to deal with diesel generators and diesel fuel in combat situations. So on this list, you're going to see this Marvel reactor, which we're building in our transient reactor test facility. And it is looking at a 2024 completion date. Project Pele is the one for the Department of Defense. And as you can see, they want a reactor that can be transportable. McCree is one of our major electric utilities in the United States. Is powered with Bill Gates's company TerraPower, and this is demonstrating a molten salt technology. And then some of these are going to be going to Idaho. Some of these are going to be going. Kairos is headed towards Washington State. Is that correct, Sean? And then this one is planned for East Tennessee near Oak Ridge National Lab. And then Natrium is planned for a small town in Wyoming that has a coal plant there, and Natrium, the reactor, is almost the exact same size. So we have a pretty ambitious next 10 years ahead of us. So our lab director came up with this slide about 3 years ago when he wanted to challenge the country to start viewing nuclear as a absolute key option. And since that time, I believe so that the U.S. views nuclear energy as a key part of our being able to reduce our carbon emissions. And so there's a lot of interest. There's a lot of political support. There's a lot of what we call venture capital, where people are investing in these startup companies. So our job as a government installation is to make it available so they can come out and test their reactors, ultimately to be able to commercialize those reactors and sell them on the U.S. market and the world market. Okay. So we've got this model of a future energy system that has nuclear generation, other energy generation, and more than just electricity production coming out of it. Clean water, biofuels, chemical processes. We're doing a lot of work to reduce the amount of energy it takes in traditional chemical processing. And then ultimately, when you see going to a more hydrogen-based economy, you have to be able to produce that hydrogen. Okay. And I just kind of hit this slide. It's a combination of, you're going to have to help me here, Sean. Efficiency, things that are low emission, using nuclear. But overall, our laboratory is going to trying to get net zero. And we're going to do that with a combination of having a nuclear generation and improving our usage of energy. And let's see. Security every day becomes more and more important. So what we've certainly seen, Sean and I have both been here since 2015, is cyber attacks are not just occurring sometimes, they're thousands a day. And we're trying to get to this, and the infrastructure in the United States, some of it is some of it is set up, where it's pretty resilient, and some of it is not. And I think that's probably worldwide. But we're not. This is state-based cyber attacks. This is a new form of warfare, and Idaho National Lab has been a leader in this for the last 15 years. So we're going to make sure that the energy systems we deliver have that built into them. And then the last thing before I get on to my MFC slides is we want to go net zero because we want to demonstrate it's possible to take a large landmass that's got a complicated mix of people, vehicles, buildings, and show that with nuclear and wind and solar, you can put this all together and it works on the grid. You know, I started my career in the power industry, and managing the grid in 1986 was very easy. You had a lot of baseload plants. You know, gas was used for topping, for meeting demand in the mornings and the afternoons. The power factor on the grid didn't change much at all. Maybe we might adjust it once an hour. And now when you have wind and solar, you're adjusting it multiple times a second. And so it's just a different dynamic than it used to be. Relative to the workforce of the future, this is one of the reasons we're here. This collaboration matters because we view ourselves as a national lab in the United States, but we also believe there's an international problem to be solved here. So, you know, having this, you know, collaborative agreement makes sense for not just, you know, for you, but for all of us also. And we want to recruit the best and brightest out of the world. So if we find a young postdoc here in Brazil and he seems eager and he thinks he can handle the cold in Idaho, then we welcome. So we've grown significant amounts since FY15, over about 1,800 new employees. And we certainly are recruiting all over the world now. So that's, our facilities are world-class. So now we're recruiting, we're getting more and more people interested. Okay. We've already talked about the directorates. This slide, you know, is pretty much the same as before, and I'm going to go into more details. By just an accident, Vivian is actually from Sao Paulo. So you know, when I was going through this the other day, Sean just pointed out that, so she works in our analytical lab, and it turns out she's from here. And I was like, I didn't do that on purpose.
Our best wishes.
Yeah, a graduate of the university.
Yep. And so I'd like to pretend that wasn't on purpose, but it just didn't work out that way. So, this is the materials and fuels complex that in which we do our basic engineering experiments for fuels, materials. There's some significant facilities here I'll just point out real quick. This is the former experimental breeder reactor number 2. That reactor was shut down in 1993. The dome was scheduled to be demolished about 5 years ago. I had a crazy idea of, let's save the dome so we can build reactors in it. And so now it's been remediated to the point where we're getting ready to add secondary heat removal, instrument air, those types of things, control capabilities, and we're going to put one of the reactors in there. This is a former reactor also. This is the zero power physics reactor. The reactor has been removed, and this building, this is all shielding on the outside of the building. This is all dirt piled up around it. That's another area that we're setting up to be a test bed for reactors. Out here in the northwest is the transient test reactor, and it is where we're building the Marvel reactor. So we have 3 different places to put your reactor based on the size of your reactor, the heat removal, security requirements, all those types of things kind of. We also have a very, very large inert hot cell called the Hot Fuels Examination Facility. That facility enables, if you can put it in a cask any place in the world and get it to us, we can bring it into this facility and do traditional post-irradiation examination where, you know, we can measure, you know, the fuel. We have a gamma spec in there. We have the ability to use a laser and pull the fission gas products out. We also have a reactor underneath that facility where we can drop that fuel in and do a neutron radiography experiment. And we're looking at doing diffraction. So that facility is what I call traditional post-irradiation examination. This one here is the irradiated materials characterization lab. This one is almost like every university materials where you have focused ion beams, EPMAs, SEMs, TEMs, X-ray diffractometers, but they're all set up so you can handle highly radioactive materials almost immediately after they come out of the core. So it used to be we'd irradiate something in an advanced test reactor and we'd wait 5 to 6 years before it could be put in that type of equipment. We've now set up a series of glove boxes and shielding such that you can take those samples, do your traditional PIE and HFEF, and then turn around and do more advanced characterization, figuring out the why. You know, this gives you the what happened to the fuel. This gives you the why it happened. And so a lot of work being done there that's never been done before on fuels and highly radioactive materials. And then next to it, there's a new facility being constructed for materials that I'll speak to here in a little bit. Let's see, next slide. This is just an org chart showing how we're organized by our core missions, and I'm going to walk through those missions right now. These are the key facilities, pictures of the inside of all those facilities, and I won't spend too much time walking through, but basically we have state-of-the-art analytical laboratory radiochemistry capabilities. We have multiple built facilities that can build fuel. We have a lot of nuclear materials that allow us to, you know, if you come in and want oxide fuels or metallic fuels or silicide, whatever types of fuels you can think of, we are not trying to become a fuel manufacturer, but we do the original demo, what I call the original recipe, and then we show that the recipe can be repeated in the right quality, and then transfer that to the private industry for them to be able to make their fuels. In our meetings here, I definitely believe there's some collaboration we can do on nuclear fuels moving forward. This is the sample preparation lab, which is a bad name. It's really going to be a materials characterization laboratory. It is the $150 million brand new build that we're doing that has both hot cells and glove boxes and the ability to direct receive nuclear materials into this facility. So there's a truck airlock that goes right next to the hot cells. So I'll be able to bring materials in. So we're going to keep the IMCL for alpha contaminated fuels, and this will be more traditional materials testing. Let's see. I think I'm going to get going. So we have a set of core competencies. I've talked about fuel fabrication. We also do characterization before and after irradiation. This is a triso fuel particle, which over the last 15 years, the Department of Energy has put a lot of effort into qualifying this for advanced gas reactors. And it's really the perfect example of not just traditional PIE, but the advanced characterization that we have been talking about, where you can see how the fission product gases are lining up on the boundaries. You can do measurements. We can actually measure the tensile stress. We can cut small features with a fib and do tensile stress testing on each one of the boundaries. And so we believe that fuel type is a key for some of the advanced reactors relative to being more inherently safe. So they're what I call a walk-away reactor. There's no, you know, once you shut down, once you scram, there's no actions needed. We do the companion materials characterization. As I mentioned, we've been doing NASA work since 2004. This started with just building the RTG for the rovers and other deep space missions. And now it's evolved to looking at a reactor, a fission-based reactor for being on the moon, and a propulsion reactor to go to Mars. We reprocess nuclear fuel from the EBR2 in order to produce high-assay LEU that can be made into new nuclear fuel. The transient test reactor is for fuel qualification. We do a little bit of work in non-proliferation and nuclear forensics, and a little bit of work in isotope production, specifically high specific activity, cobalt-60 irradiated APR. I mentioned radio analytical chemistry. And this last one, the division that does our basic research didn't exist 7 years ago, and now is the division at the laboratory that publishes more papers than any. So when we've been visiting, visiting with your facilities, it doesn't take long once you decide this is what we, if you build out the facilities, people come. When we built IMCL, nobody even knew what it was. We started publishing a few papers, and now we're recruiting. We've got scientists from Italy. We've got scientists from Asia. I mean, they see the capability, and everybody wants to work there. So it didn't take long for that to turn around. These are some of our critical outcomes for next year. We want to deploy reactors. We want to continue to fabricate fuels, do our radiation testing. We also continue to support our NASA customer. And then we have a big role at MFC in dealing with our back-end legacy items from previous work and making sure that every reactor that we look at, we're taking an approach of, we want to help the reactor builders from the time they want to pick their materials to the time they want to dispose of their waste. And so that's a pretty large portion of what we do. It's not my part that I like to do, but it's in my organization. So I'm kind of stuck with it. But no, it is important that when you build advanced reactors, you have a plan for the disposition of the waste, because that affects the cost. And MFC has about 900 people on site. We have 29 different nuclear and rad facilities and 2 reactors. And we're completely connected into all the things that the ATR is doing on the radiation and nuclear science and technology. So the modeling and experimental connection is, I generally have a rule of thumb. If we're doing an experiment, we should be modeling it. If we're doing modeling, we should be doing experiments. Those 2 things are incredibly important for us in the long term, because we'd like to get to the point where some of our models are so sophisticated that your licensing process can be really enabled by modeling. But as we spoke yesterday, nothing beats an experiment that makes your model look terrible. Okay, so that's a good thing. So our models are very, very precise, but sometimes they're very inaccurate. And so what we're trying to do is make sure everything that we're running in the model is backed up by true experimental data. I'm going to go quickly through these slides. There's a ton of information. We'll certainly make these available. We are doing some additive manufacturing to make fuels, which is exciting, because I think we can get geometries and we can lay burnable poisons in the fuels. We can do things that you just cannot do with traditional, but there's a lot of development work to be done there. Uranium likes to catch fire when you put it in a powder form and try to put it in a traditional 3D printer. And so we're trying to bring our expertise relative to handling uranium and our expertise. And so we've made a lot of progress there. We are proposing to our United States government to build a new reactor fuels research laboratory. I wish I'd have proposed that 5 years ago, because I need it now. My fuel capability is maxed out. I mean, every corner of floor space is pretty much spoken for. Transient testing, again, this reactor is a 1957 reactor. It had not operated since 1992. The reactor was in very, very good condition. We did a restart effort and started it in 2018, and it is booked solid. And this reactor allows you to go up to 17 gigawatts in a very short amount of time, and we fail fuel in it. That's the purpose of this reactor, to see how fuel is going to handle during extreme conditions. And that, we believe, is proving to be a big part of qualifying fuels for these advanced reactors. Again, experimentation versus modeling and simulation. Spoke about the analytical research lab. The reason Vivi and others is we've now got state-of-the-art equipment. and we are bringing staff from all over the world that have expertise. So the characterization in advanced PIE, we're now getting, to the atomic scale and looking at some of the phenomena that for many, many years, people, knew that we got these macro, that when you did PIE, you knew we were having problems, but now we're starting to understand why, and we're learning things that, quite frankly, aren't modeled correctly. And so it informs our our decisions on how to design advanced fuels, and it also breaks some old paradigms that we all thought we understood pretty clearly. Again, post-radiation examination, HFEF is one of the biggest and most mature facilities in the world, and so that allows us the opportunity to try different things. We're now to the point where we've taken some irradiated fuel, recycled it, reprocessed it, put it back into Sean's reactor, and then redone the PIE, and we're seeing what's the difference between starting at ground zero with something that was unirradiated and starting with something that now you're recovering the materials, and we are seeing differences there too. The NASA work is fun. Unfortunately, due to COVID, and I was supposed to be there for the last launch, but the amount of people allowed on site kept shrinking and shrinking, and it was just a small group of people that were there to watch the last Mars launch, which happened in 2020. And then we are making a lot of investment at MSC. In the last 7 years, with our capital construction projects, we've probably invested about $200 million at MFC, $200 million. After we finish SPL, and then we move on to the test beds, and we probably have plans, we have plans to invest about 500 more million over the next 5 years. So it's a very ambitious build out, but again, the U.S. sees nuclear as very important. And this is the material management. We have built a repository out near Sean's facility, just upwind of Sean. We built a place that is for some of our remote handled low-level waste. And then we are doing R&D in this area to figure out how to reduce the cost of handling some of these materials. And that's I think there's probably I don't see it up here. Maybe that got edited out. I'm not sure what I can share and I'm not, but we've had a couple innovative things that are really helping us from the traditional break it down, package it, bury it in the ground. So it's, obviously with a facility complex this large, being able to do maintenance, maintain that infrastructure, and fabricate things for these advanced reactors. This is a mock-up of the Marvel reactor. We're going to run this with an electric heater before we actually build the final product, which will have the nuclear heat source. And with that, we continue the balance of executing our investments, improving how we do business. We think is important, delivering our mission outcomes. We've got a lot of projects, and then dealing with our waste. And now I'm going to turn it over to Sean, who hopefully will sound better than me.
Ron's a little congested today.
I feel great. I don't know what the air here in Sao Paulo is doing to my throat, but it's not good.
All right. So we're going to talk about the advanced test reactor. The advanced test reactor is a 250 megawatt thermal reactor. It's the largest, highest power test reactor in the world operating today. What we have here is a picture of inside my reactor vessel during a recent overhaul over the last year. We went in and replaced everything within the reactor that would be called a reactor core component We call this the core internal changeout. We have to do this about every 10 to 15 years because the high neutron and gamma fluxes inside the test reactor, as we're testing materials, we're also damaging our own reactor. And so because of that, the reactor has had to go through 6 of these overhauls in its lifetime of now 55 years. And so what we see here is one of our technicians in there inspecting an in-pile tube, a stainless steel tube that we use for simulating the conditions of a nuclear power plant pressurized water reactor of 3,000 megawatts. Okay. So the advanced test reactor and that complex that we used to call the test reactor area has been around since pretty much the beginning of nuclear power development in the United States. The first reactor that started up of the 52 at the Idaho National Lab was the experimental breeder reactor number 1, but almost within a year, the S-1W Nautilus submarine prototype was started up, and down the road here at the test reactor area, the materials testing reactor was started up to begin testing materials for the Navy and for nuclear power energy development. Someone in the Navy test program has told me many times, once you start up a reactor of any kind, you immediately have to start developing a test plan to test the fuels and materials, because as we say, these test reactors are time machines and accelerate the damage that will be seen during a normal lifetime. So you can test fuels in an environment that is prototypic of the environment that the fuels will see in actual use, but the accelerated burnup, you can see those results 10 years or even more before they see it in an advanced plant. So here, the advanced test reactor, the small picture on the left-hand side is when we had 3 of our test reactors running in 1970. The materials testing reactor at 40 megawatts, the engineering test reactor in the middle of the screen, in the middle of that picture at 175 megawatts, and then the advanced test reactor, which is off by itself in that picture at 250 megawatts, also running at full power at that time. Typically, ATR will run at 120 to 105, 120 megawatts. The reason is because the high power will literally destroy fuel samples well before you can get any data, which provides no value. So the facility on the right hand is just a picture of the complex today. You can see, as Ron's picture, we are out in the desert away from Idaho Falls. Characteristics of the advanced test reactor, I mentioned the power level, of course. It's been operating 55 years this month. High neutron fluxes, 1 times 10 to the 15th thermal flux, which is one of the highest flux reactors, comparable to the high flux isotope reactor, which is 2.5 times 10 to the 15th. But the fuel arrangement and the unique design really makes the advanced test reactor so unique in the world of test reactor development. It is specifically built to test nuclear materials and fuels for nuclear power development and the United States Navy. Specifications here, you can see the reactor vessel there. It is a solid stainless steel vessel, the only type of vessel in the world that is not clad with stainless steel or other materials. It is solid stainless steel. That reduces the likelihood of embrittlement from irradiation. It's designed to have a long lifetime. And our current estimates with damage and the current fluence rate on the reactor vessel, our estimates that we could probably run for another 300 years without having to change that reactor vessel. It is 12 feet in diameter, 36 feet high. You can see the characteristics here at the bottom of this slide. It runs at 71 degrees Celsius is the maximum outlet. So it's basically a hot water heater. It doesn't run at high temperatures. It doesn't boil the water. And it is pressurized to 390 pounds, 2.7 megapascals. So it's slightly pressurized. So how do you simulate the environment of a nuclear power plant pressurized water reactor in this sort of environment? Well, we have the in-pile tubes, which I'll use my laser here. We have in-pile tubes, those stainless steel tubes I showed you before in the photograph, that inside those tubes, there's a flow tube. It is a single tube with a center tube that goes up with flow and an outer tube of envelope that goes down. And we raise the pressure to 2,500 pounds 3,000 pounds of pressure and high temperatures, 500, 600 degrees Fahrenheit, very exactly as you would see in a pressurized water reactor, including the chemistry. So as far as the sample of fuels or materials, that is in a high neutron flux, and the conditions are exactly as that sample would see in a nuclear power reactor. And that's how we simulate those conditions in the advanced test reactor. This is another picture of the advanced test reactor. It gives you a size comparison. It is 1.2 meters in diameter across and 1.2 meters high. The fuel section is 1.2 meters available volume for irradiation. Again, you can see the size of the operators here. This is during initial construction. We do not load fuel by hand like this anymore. It's a little dangerous after 55 years of operation. The curved tubes off to the left and the right of this photograph are neutron instrumentation tubes. They are curved, of course, prevent radiation streaming out of the reactor. And then you can see next to these two technicians, the in-pile tubes extending to the top of the reactor to load these very large experiments. So very quickly, I'd like to explain why the advanced test reactor is considered so advanced. Advanced in 1967 when we started up, and still considered the most advanced reactor, test reactor operating today. You see the yellow in this diagram on the left. The yellow are the curved fuel plates, the fuel elements, which I said are 1.2 meters tall, 19 fuel plates. It's a highly enriched uranium fuel system. It's very similar to your 5 megawatt reactor in terms of the fabrications, powdered and rolled materials. But it is highly enriched uranium because of the high power density. We have not been able to convert it to low enriched uranium at this time. But the serpentine fuel, this four-leaf clover shape, wraps the fuel around the experiment locations in orange, creating these very high neutron flux density flux traps. And this is where the experiments, the key experiments for power reactors, the U.S. Navy and the U.S. fuels development are in these areas. The purple circles that you see in there are embedded positions and holes inside the beryllium reflector. Beryllium surrounds our advanced test reactor, which is how we operate the powers we do. So we have 77 positions that are available. The advanced test reactor is so utilized at this point for testing materials and some cobalt-60 isotope production that 90% of our key locations are scheduled for the next 5 years, with many of these positions also scheduled for an additional 5 years, so 10 years out. The United States Navy uses us as their test reactor. So we have been testing fuels for ships, submarines, and aircraft carriers that are in the fleet today. Due to the testing of materials in the advanced test reactor, the U.S. Navy now has ships that have life of the ship cores. They never have to be refueled because of the density of the energy density of their reactors. That is a 40-year operational ship without ever having to change the fuel.
Plutonium-238 also.
Thank you. Ron put a plug in for NASA. We also make plutonium-238 for the NASA missions. We and the high flux isotope reactor at Oak Ridge National Lab are the production sources of plutonium-238 in the United States. The way the ATR works, very quickly for the nuclear engineering folks, these gray circles in this picture are beryllium cylinders. They are also 1.2 meters tall. On the there's a 120-degree black band on these cylinders. That is a hafnium, the strong neutron absorber, a hafnium. When the reactor is started up, these cylinders rotate away from the reactor, taking the hafnium neutron poison, neutron absorber, away from the fuel, and the advanced test reactor will start up as these cylinders rotate away from the fuel. That allows the entire 1.2 meters of height to be available for irradiations from the minute that the reactor is at power. Unlike many other reactors in the world, the effective height of the advanced test reactor is always 1.2 meters of available neutron irradiation space. This is the Advanced Test Reactors reactor control room. It is taken with the camera so you can see the entire room. Typical 7 days a week, 24 hours a day. We have 5 rotating shifts of reactor operators. A typical shift is 15 persons due to the size of the reactor, as well as you can see that the facility is all out by itself. So we also maintain potable water systems and other systems. We are effectively a city of 500 people out in the desert. The condition, you can see very flat screen monitors for instrumentation. All of these were upgraded in the late 1980s, early 1990s. We are currently doing upgrades of the systems to ensure cyber protection of the facilities as we convert to digital, as well to just replace computers. As we all know, computers don't last a long time, and after 30 years, some of the computers completely obsolete and no longer available. So we simply have to upgrade to maintain current. The overhaul that we just completed was highly complex. The most complex overhaul that the Advanced Test Reactor has been in its 55 years, with the exception perhaps of initial construction. We performed a significant work on the reactor and significant life extension, age management work outside of the reactor core itself. The U.S. Navy and the Department of Energy have determined that the capabilities of irradiations that the Advanced Test Reactor currently provide are necessary for the next 60 years. They have already told us these facilities, this thermal irradiation capability must be available to the United States to 2085. That would make the Advanced Test Reactor a 120-year-old reactor. So we are looking at options to perhaps replace these capabilities in the next decade or two. But for sure, the Advanced Test Reactor is not going anywhere for at least another 20 years. This was a few pictures from the overhaul. To actually access the core the way we need to do for this overhaul, we have to take the lid of the reactor, this reactor vessel head, which weighs 30 metric tons of stainless steel. That head is removed and placed on a stand off to the side of off the top of the reactor. And so this is how we'll access the reactor. 3 phases. We take the lid off, take all the internals out of the reactor, highly radioactive materials. Some of those materials have to be transferred through air. We completely empty the building when we do those transfers, obviously. And then we put the lid back on and put the reactor back in with new components. And so we are very proud of that successful completion. We took tours of your facilities. We also have some experience in upgrading our second reactor in the building. We have 2 reactors, as does Ron. We have the Advanced Test Reactor at 250 megawatts and a critical facility that we use for testing of experiments and materials prior to going into the big reactor, and it only operates at 1,000 watts. But it is identical in size and shape and configuration to the Advanced Test Reactor. It just does not have to be force-cooled because of its lower power. And you see here in these pictures, we performed a significant digital upgrade to the reactor console for the Advanced Test Reactor critical facility, ATRC. Now about 3 years ago, we completed that project. We're continuing to upgrade some portions of the ATRC console, but this is a significant improvement too. So we've already discussed sharing some of our experiences and perhaps having some of your staff come visit to see what we've done with the Advanced Test Reactor in upgrades of our components. I mentioned our customers. Obviously, the United States Navy's nuclear propulsion program for aircraft carriers and submarines is a very important program. We are developing fuels and materials for the next generation of submarines. That work is going on right now. But it's important to point out that 50% of our work is just to support the current ships in the fleet. Ships that have been operating for 25, 30 years still need nuclear materials testing. And I think this is an important point for both Ron and I to point out that as long as you have operating nuclear facilities, you need to have the ability to test those materials in an environment that is similar to that condition as well as being able to perform some level of post-irradiation examination. And so this is part of our support for not only the current operating fleet of reactors, the U.S. submarine fleet, but also the advanced reactors that are going to be coming online in small modular reactors in the future. One program, this is an example of our in-pile tube, our pressurized systems. They're effectively very small pressurized water reactors. They cool and heat the material, but the volume of coolant in this entire system is less than 200 gallons of liquid. So they're very small volume, very small circuits that circulate materials or circulate coolant. And we are currently developing an even smaller system of circulation due to the needs to do these irradiations on the periphery, on the edges of the advanced test reactor core for ramp testing and some similar conditions that we discussed about the RMB reactor design to simulate some conditions necessary for fuels testing. Thanks. Just a typical sort of capsule. Again, advanced test reactor, this experiment test at the bottom of the slide here is 5 tiers of different materials and samples to be tested. And all 5 tiers are available because of the design of the advanced test reactor. We don't have to adjust for neutron flux densities as the reactor operates. The entire volume is available for testing as soon as we start up. Ron mentioned the TRISO system. You can see a pile of the TRISO fuel particles there in that photograph and how they're encapsulated in fuel pellets for high temperature gas reactor and other uses. We did the qualification of the TRISO fuel system in the advanced test reactor. And I mentioned that we use pressurized water systems. We can simulate that. In this case, we had to simulate the conditions of a high temperature gas reactor that is a fast reactor. So we simulated that condition by flowing helium gas through these particles, these samples, to simulate helium gas coolant. And we also, let me see if I use my pointer here. We also, you see, we had a ring of hafnium as a neutron shield, a neutron filter, to remove the thermal neutrons from the test. So the fuel particles, as far as the fuel particles were considered, if they actually had a thought, the fuel particles were in the environment of a fast, high temperature reactor, and that's how we qualified the TRISO fuel system. So we can also do other coolants. Finally, some of the materials that we're testing today are advanced manufactured, 3D printed, advanced manufactured materials. And this is an example of one of those where you could not possibly manufacture something with these geometries with any machining available today. So this is a 3D printed stainless steel component that could go into a advanced power reactor. And these materials you have to also test to see how they perform under long irradiations. It is the 3D manufacturing process and the sintering gives very interesting stress characteristics of the material that is not modeled very well at these points. Finally, ATR canal area, you can see where we move our fuel and as well as our experiments, and we're currently using some of our material recently irradiated fuel. You can see these on the right-hand photograph there. We take material fuel directly out of the reactor and put that around what we call a gamma radiation tube, which is roughly 10 centimeters in diameter. And we can put materials down if only for a very, very strong gamma source. We've done cameras and borescopes for very high radiation environments for cameras, as well as performing some experiments with some of these advanced reactor coolants, such as molten salt or liquid metal for radiolysis. And that is all I've got on the advanced test reactor. Thank you very much for your time.
We thank you for this great presentation. It's remarkable PR infrastructure and so on. Posso diminuir aqui? É isso? Okay. Before open the question, I have a broad question. You have we see you are increasing all your program, and you have a military investment, special, but as far as I can understood, your main drive is the climate change. It's right, and do you think this is a way for development of a nuclear program?
Yeah, I would say, so the U.S. never really stopped doing any nuclear R&D, but certainly the climate change issue has been a catalyst to understand that nuclear is a solution to that, and that's probably been proportional to the investment. So yeah, it is probably one of our primary drivers. You know, I'm a nuclear engineer, so it's the best, you know, and so, I mean, I don't know. You got anything to elaborate on that answer? But
so obviously there's been ongoing development in nuclear power plants, the AP1000 and other systems that are being built now. The smaller modular reactors began with a smaller version of that, but then as we see climate change being more and more of an issue worldwide, we see small modular reactors and large reactors where it makes sense to be part of that solution. And where the laboratory is, the Idaho National Laboratory, we want to show our own country that you can go net zero, almost carbon free, but you need to use a nuclear reactor. You cannot do it with wind, you cannot do it with biomass. You cannot run a high technology industry on wind. It's just not reliable enough. And so that's part of our showing that. So that, yes, it's starting to accelerate as we start getting into vendors who are looking at smaller reactors than the big reactors, but we still have a lot to do with the big reactors, because where it makes sense, those are part of the solution. So yeah, I think that's all true.
Thank you. It's open to the questions. Someone, Rota.
Você vai mudando? José Perrota from IPEN. First of all, thank you very much for your nice presentation. I feel like we are in a kindergarten, you are in postdoc level, right? But as a big installations, right?
we were in kindergarten just 7 years ago, so we had, you know, so it's.
Yeah, because looking to the kind of installation is very different from what we have. But anyhow, the philosophy and the main things for develop the nuclear technology and the goals of the country, you showed that you have to invest. And I saw that you are going to invest a lot of money for this, and also a very important thing, newcomers, new scientists and new technologies come to you to work. And so if you have to go to ATR for 2080, right? You said you have, it's 2 or 3 generations from that.
Yes.
So you have to start now. And I'd like you to give a message on this, please.
So
well, it's good for us because here we are in the opposite side, and the people we are losing scientists, we are losing technologies. You see, you said you have a young postdoc here that you'd like to have there. Yeah, because we'd like to have many of Alexandres in our, please. So,
so I've been in the nuclear in this function since 1992, okay? Because I was at Oak Ridge at the high flux isotope reactor. And so I got to see the US in that same dip. But what's common between the US institutions and here is you have a long storied heritage of doing great nuclear work here. I mean, just walking around this campus, you've got the hard parts. You've got the reactor, you've got the facilities. And I'm hoping what happens in your country is what's happening now in ours is young people think nuclear is cool. There's less and less people that are afraid of it. I mean, I think we're at like 70-some% of the country now believe nuclear power has to be part of our solution. And so traditional, nuclear engineering schools had really dipped down. The one I went to shut down after being in business for 60 years. And so we're seeing that turn. And then also you're seeing, so the nuclear technology hasn't changed that much. And you know this better than I. I mean, you look at the reactors we're choosing, they're reactors that were demonstrated and proved in the 60s or not proved in the 60s, but now you're bringing to bear additive manufacturing techniques, new control systems. I mean, new technology that makes that companions well with the nuclear technology. It does present some new problems like the cyber challenge, because, an old reactor can't be hacked because there's nothing to hack, but the new ones can. But we are seeing this renaissance in a variety of ways, in that, it is great that even in the 7 years that Sean and I have been here, it was harder to recruit in 2015 than it is now. In 2015, I had to convince people two things. Hey, nuclear is really good, trust me. And moving out west into Idaho is and now, fortunately, a lot of our students think that moving out west is cool and nuclear is cool. So they're coming at it from more than just traditional nuclear engineering programs. And so that's a good thing. And, but that history and that heritage, and the fact that we didn't have such a dip that we lost all of that, we still stayed connected. That's important because you need the knowledge transfer, you need the mentoring. And I think we're in a spot now where we're getting that. So, Sean, you got anything?
No, not really anything to add. It is, we are getting, again, for recruiting, because so much is going on at the Idaho National Lab in nuclear space, and that, you get the buzz. People see it they hear it in the schools. They see it. We're getting people who are sending us resumes for positions. Just say, here's my resume, find me a job. I'd love to work somewhere there. And so I think there is an excitement about it. And Ron, one thing that Ron said that I think is very important that we've seen is the generation that we have that are in college now today, they are looking at the world and saying, how can I make the world a better place? And so they look at that and they go, okay, nuclear power, my parents don't like nuclear power, but why? Let me understand it. It has to be because the same argument. Wind and solar are great, part of the solution. Biomass is great, part of the solution. Hydropower. But if you want high energy density to provide reliable power, carbon-free, nuclear power has to be part of the solution. And when the youth come to the conclusion themselves, their excitement propels them in this direction in some way. And
I would even say this, even I had some biases when I came in 2015, because I love big 1,000 megawatt electric nuclear plants. They're proven, they're easy to run, they're extremely reliable. 94% is the average for the industry in the United States. So when people said, well, let's build a small modular, I said, well, you're taking away what nuclear brings from the technology, in that the fuel cycle is what makes it, I take an area this big, I put fuel in it, I put a lid on it, and I run it for 2 years. Shrinking that, just, you keep the cost, but you don't. But then people are seeing nuclear now as, well, you've got a bunch of 200 megawatt coal plants scattered in the United States. Wouldn't it be nice to be able to build modular reactors in, Wisconsin and just ship them to those plants, pour some concrete and start running it? I said, all right. And then the micro reactors, I was even more skeptical of. I was like, why would I build a 10 megawatt electric? Where you see the example where our Department of Defense says, boy, it would really have been nice in Iraq to be able to deploy reactors instead of having to set up power lines and diesel generators and transport. We had a presentation where they said more than half the casualties in Iraq from in the US were logistics trying to lift power and water. Now, you apply that to, okay, I'm not a military person, but you've got remote communities that are off-grid. You probably have them in Brazil, where a small microreactor that is literally what I call a push-button reactor, it's the kind that we think we're going to be able to operate without operators. The cores are so small, the systems are going to be relatively fail-proof, and you can push in and plug in, and you don't have to figure out, okay, how am I going to do this in a place that's off the grid? And that honestly is more young people coming in and thinking of it differently than, you know, someone who is not as young as I am. You know, but that's an, you know, so it's the technology plus it's the adaptation of the technology. People are thinking differently. You know, our senator from Alaska, when she saw this, she was like, this makes perfect sense. You know, the Canadians have 350 cities that are off grid. And you know, and I was visiting them and they're showing me this map and I said, I don't even know where Canada ends and Greenland begins, but boy, I didn't know anybody lived in those areas. But so those kind of logistics, which are extremely difficult now, could be made really easy by nuclear power.
They survive by diesel fuel delivery to their generators.
And we've got this perfect example in the US. The Naval Reactor Program has spent 50 years developing not 50 different types of fuels, but just keep improving theirs. And so you can continue to make it better and better and better by bringing this to bear. And we're going to try to do the same for our power industry and other applications. So
that's nice, because this kind of fuel development is very important for the new generation. Also, you showed here the space, space and the moon and the Mars. It's nuclear. Yeah, you cannot have wind or diesel or something. It has to be nuclear.
Yeah, when you look at it,
is in a good performance, and you have to study, you have to develop, you have to have an infrastructure to develop this. And this is very, very important.
Yeah, and it is fun doing the NASA work. And it is fun of thinking about, okay, if we're going to get to Mars, we're going to have a lunar, you know, you're going to have a lunar presence, because you're not going to launch from the Earth and make it to Mars. So they're looking at, okay, we're going to launch from the moon. But to do that, you got to have a power source, and fission power up there makes a ton of sense. So,
and also a fuel that is, like you mentioned, your submarine once through life fuel, right? This is technology. This is development for having this, right?
Yep. Yeah, we're mixing a lot of some of the advanced reactors, some of the NASA work. They're all looking at the same fuels types. You know, I mean, we're getting good crossover there. And as the nation's nuclear lab, that's what we bring to this, where, you know, hey, you don't have to start at zero. You can start by taking the TRISO fuel pellet and looking at your reactor system for that. So that's what NASA's doing right now.
Just another question. You mentioned here you do fuel material development, fuel and material. Radioisotope production, some of them with high flux reactor. You mentioned cobalt on other things, right? I didn't see here the neutron beams utilization is in the other reactor.
Yeah, so the high flux isotope reactor, which I used to run, has a big neutron scattering program.
Okay.
We have the ability with that reactor that's buried underneath my hot fuels examination facility. We've got one beam line right now that we're doing all our neutron radiography on. We have another beam line that we don't use, and we want to use that for a diffraction beam line on extremely highly radioactive materials. So we would love to be able to do some neutron diffraction of the things that are in the hot fuels examination facility. So that nobody really considered that until recently, and we're like, okay, that makes a lot of sense for us. So, but just one beam line.
Okay, just the last question, not a question, but asking you to say something about, we are in the kindergarten But what do you think about the proposal of R&B reactor here for us?
Well, I mean, I love it. I mean, I don't know what, I think it's essential. I mean, I hope, you know, as we've talked this week, you know, we'd love to see, you know, all the Americas kind of come to a, you know, I mean, you've got a great heritage. We were just in Chile. They have a great, you know, heritage. You know, Argentina is kind of kept theirs moving. I think it's important. I think nuclear power, I think in 100 years, there won't be any debate. You know, when I speak to college students, I tell them 100 years from now, all the electric will be nuclear, hydro, wind, and solar. And we won't be, you know, I mean, there'll be a little geothermal maybe here and there, but there won't be any politics to discuss it. You know, we won't be burning what I say, you know, I use the term burning dirt. We won't be burning dirt anymore for our power. And we got, you know, and, you know, clearly what you've done here was incredibly important. And the idea of let's recapture that, you know, again, you know, I wrote my first paper about nuclear power when I was a sophomore in high school. So that's now been 40 years ago. And I was like, this is the magic thing. This is it. And so I think, you know, without getting, and I don't know your politics, but, you know, any sovereign nation has to look at nuclear and the nuclear technology and say, we've got to be part of this. And I tell people, and this has nothing to do with Brazil, I said, people take for granted in the United States that we're indestructible, that our sovereignty is never can be broken. But when energy is not right, and you're seeing it around the world right now, I mean, when energy is no longer, you know, relatively cheap and extremely reliable, governments fall apart. And I said, we can't be so arrogant that we can't think that if we're not thinking progressively about how we're going to deliver energy, that it's not something that, you know, I mean, energy goes with water, which goes with food, but you got to have the energy first. You know, the other things are all byproducts of it. So yeah, I think it's an incredibly good idea. And the reactor design, you know, even though it might not be as good as HIFER, you know, it looks better than ATR. How's that? I can't help myself. Yeah.
You're such a good friend.
Yes, yes.
Oh, okay.
Thank you very much. Thank you.
First of all, thank you very much for Ryan's presentation. My sensation as a researcher, and most of us here, engineers, physicists, it's like a dream. Because we have been working hard to assemble such kind of facility, mainly for study some material before and after radiation. Because there are some requests from different private companies also that they want to evaluate this material. They produce nuclear few elements for the Angra 1 and Angra 2, for example, corrosion and so on. And that is also one research center in our institute. Formerly you visited after this presentation, after the discussion, that we need to evaluate some materials, for example, some components that I want to talk with about this, Dr. For example, we have the technology now to assemble some targets to produce more than 99. It will be very important for the Brazilian multipurpose reactor. And you notice a lot of possibility to use your facility, the RTR, and also to evaluate materials before and after radiation. And my question, is it possible to carry out some collaboration? Because we have an agreement with our institute and Batelle Alliance. If it is possible, how the way, for example, it's necessary to propose a project together with your institutes or organizations, need to have some budget from Brazilian government or the US government to carry out such kind of development. I'd like to know some solutions for this. It's possible or not, evaluate some material with this proposal, mainly for research and development, and radioisotope production, for example. and also how to carry out this project. Specific project, we have a budget for this, we need to provide this budget. Please, do you have some?
Yeah, certainly. You know, it's hard to get an irradiation into the advanced test reactor. I mean, but the things that we do at MFC, probably 80% of the work that we do is open published. There's no issues relative to, you know, there's no government restrictions on the data. Okay. So that's not an issue. Some of the things we do for private industry, they want to hold their own, you know, intellectual property. But if we have a good idea and we want to propose this together, yeah, that's well within what we've done. I'm trying to think of any relationships we have like that already. Yeah, we had a fast reactor test program with the French for a while. Thank you. We had a huge program with the South Koreans that what I was talking to before was called the joint fuel cycle, where they recognized their inability to have a lot of nuclear waste, and so they wanted to reprocess their fuel. And then that's the experiment that we ran, where we took fuel, irradiated it, processed it, pulled it out, repackaged it, and re-irradiated it, and then re-examined it. Yeah, it was a multi-year, it's a 10-year. The joint, that was the Department of Energy owned that one, I think. But we have a different mechanism. We have CRADAs, we have other mechanisms. They're not quick. They don't, you know, there's a lot of, I got to make sure I don't say anything. There's a lot of lawyers involved. We have great attorneys, by the way. You know, Kimberly, our general counsel, is fantastic, and she's of the mindset of trying to provide solutions. And so there is a process the government has us follow, but we've done it before and we'd love to do it again.
And there, so
you are going to visit the center now,
Yes.
just now, and I think she can show you the target.
Yeah.
And it would be lovely if you could do that together.
okay.
Yep.
Okay? Yeah, you're going to be together with them. Okay.
All right.
And then other things we talked about, you know, the advanced characterization, those things are, you know, on little I mean, those are very small. That type of thing where you'd say, hey, send this and we can examine it. Or, you know, you bring, you know, a few of those targets and you bring a student. Those should be very easy to do, very easy to do. So.
It would be something that we will be very pleased if we can really achieve it, because these people, these researchers, have been looking a solution for this for many years. Where to really radiate and to test, and if it is okay, they will be has been, I think, following this, no? Have you been following this? Because this is something for R&D.
Yeah.
So if you please ask her to talk about it. I have one question for you that's concerning
we have samples irradiated in our reactor. We do non-destructive analysis, but we do not have hot cells to look inside. Right?
So we have shipped things internationally. So it's not, we just have to work out the logistics of what it takes to get that packaged and sent. And I say that it's never the technical issues, okay? We've had things sit at the border for months and months and months and months of a particular place, but we just need to work through that type of thing if you need.
The easiest way is to send a non-irradiated target, irradiate it, and do the post-radiation.
Yeah.
Not to check.
If you have a target that's not irradiated,
yes,
you know, and again, depending on what you need, there are a lot of spots in the advanced test reactor that are lower flux, but they're still very high flux.
Yeah, so 30 megawatt equivalent flux.
Yeah. So another.
No, I just have a question, how you manage and how you deal with the disposal of the burnt fuel? For instance, since the security, since the license, where to put this, where to deposit, how is it happening over there?
So the U.S. does not have a final repository designated yet. You know, we put a lot of time and effort into Yucca Mountain, and then that became a political, you know, we don't want it in our state. So what we do now is our policy is every time we go to irradiate anything, we look at the material and say, yes, this is, whether it's fuel or any type of materials, we come up with a waste disposition path. And if it's something that doesn't have a final repository, we typically just get it packaged to the point where it's ready to go, ready to be shipped. And so, yeah, that is still one of our biggest issues in the United States. Is it's not, again, not the technology, but determining what's, you know, the department saying, okay, we've got a path forward on final repository. I would say I'm relatively optimistic in the last 7 years that we've all kind of reached a, you know, that it was one party had one opinion and one party had another. And now I think the idea of doing siting in places where they want it is probably where we're going to end up. And
we call it consent-based siting, where rather than forcing it into a location, you ask a government, a city, a state, would you be willing to have this waste site stored here? Here's the parameters. And so that seems to be gaining ground, where you are renting space from a city or a state.
And a midterm repository where you just take it and you put it someplace for 100 years, makes it a lot easier to handle. So we're doing a lot of R&D on that, make sure that, yeah, if I take an aluminum-based fuel, if I put it in a cask for 100 years, when I go to handle it, am I going to have something I can still handle? So there's work being done there. We've made a ton of progress with the Idaho National Lab has a bunch of fuels from all those old reactors and other reactors. And so people are starting to look at those as not just a waste issue. Some of that we're looking at recovering materials out of. We're doing R&D at the lab. It wasn't on the slides, of trying different processes to try to do recovery. For like advanced test reactor, which starts at 93%, when he's done burning, it's around 60. So there's a lot of good material there. So the dialogue is becoming, and the work is becoming more of a technical approach again. And I think that's a positive.
Is it the same bodies with the radioactive sealed sources?
So no matter what it is, we look at the materials and say, if you want to irradiate this, when you're done, what's my disposition path? And we have to calculate and figure out, okay, this is a reasonable path for this, and this is how much it's going to cost. And depending on how long it is, we set that money aside so we don't create another legacy pile. Those are the metrics that the Department of Energy sends me every year, that they want to see my legacy material going down. And we've literally, I don't know how many tons we've shipped. A lot of material in the 7 years I've been here. We're making good progress. So whether it's a source, whether it's something we've irradiated for materials test or a fuels test, we have to figure that out before we go forward with the experiment.
Well, it's okay. I think it's okay. We have 1 hour and a half, I think. 1 hour. So thank you very much to everybody who is watching us. This is going to be available, this recording. So I thank you very much. It is very good to have this good news from you that things are going up. You know, the number of people, they are employed, the great and growing interest of the young people in nuclear. So we have at least some good news that maybe Carl can let us know about this. We are starting a new course in the University of São Paulo, that's nuclear engineering.
Great.
So I'd like to really ask your help how to change these biased ideas on the nuclear energy.
Yeah.
Because this is very hard. I think even for irradiated food, so maybe how we can talk a little bit, but we need some help.
Yeah.
If you are having some progress with that, I'm very happy because I'm not really optimistic.
I think the biggest thing is people are having their lights turned off in the US. You know, they're doing rolling blackouts and they're going, I need power, okay? And so that helps a lot when they don't have any power and it's 100 degrees Fahrenheit. That seems to convince people that maybe we ought to be, you know, looking at this again, so.
So I'm very impressed by all the presentation. I'm very happy we are now partners, so we can collaborate. And I think that we are in this situation that we are now, we should really be using your facilities to improve our knowledge. And then you are talking to the people here.
Right.
That's the best people to talk about it. So we hope for the future. And thank you very much for bringing us some hope.
Well, thank you so much for having us. It's been a delightful visit. Appreciate all the, well, and I would not downplay the expertise you still have here. It's been impressive. So, and this campus is impressive. So, and I think you have, you know, you're very close.
Yeah.
Thank you.
Thank you so much.
Thank you.
Is it possible to have this presentation copy of that?
Yeah.
They've got it.
Thank you so much. It's, we are very proud to have this opportunity to collaborate with your institution. And there are a lot of possibilities. And I think this idea to put together the Latin American country, for example, Argentina, Brazil, Peru, Chile, and show us the possibilities of nuclear technology in terms of materials, defense, better life, energy, and so on. I think it's really very profitable. And I think in our case, in our institute, during this visit in the research center, I think we need to find out possibility of collaboration. For example, to establish some project together with PhD students, for example, to carry out some experiment and also to find out the way to support this activity with a project from São Paulo state government that supported this or the Brazilian government to carry out such activities. I think it's very, very important. But anyway, I hope that you enjoy our facilities also. Also, they are available for collaboration. If you would like to send some researchers or students or so on to stay with us, we receive a lot of experts from the International Atomic Energy Agency, mainly in the region and abroad also. To stay with us 1 month or 3 months. Everything is available also for our institutions.
Great.
Okay.
Excellent.
Thank you so much.
Thank you. Thank you.
Congratulations.
Vamos encerrar aqui então a apresentação. Obrigado aí pela presença de todos, pela audiência. Marisa?
All right. They used it.
Tinha alguma